Hello and welcome once again to the Waters and Stanton video channel. My name is Peter Waters and my ham radio call sign is Golf 3 Oscar Juliet Victor. Hope you're enjoying your ham radio hobby, and on this channel we talk about various subjects and we have various features, and something we actually added very recently was a special discount to viewers for this channel. That's right, if you view this channel you can obtain a discount provided you order from our website. Now, we published a video a couple of days ago giving you details of the discount code. That code usually lasts for several days, then it will expire and we will then introduce another discount code. So it pays to keep in touch because you can save a substantial amount of money. So please do check this channel regularly and look for on the title page. You'll see the title page will very clearly show that there's a discount code in that video. All you do is you copy that discount down, and then when you go to checkout on our website, just enter that code, and provided that it's in date, because we do give details of the starting and finishing dates, provided it's in date, that code will automatically take a discount off of the total amount in your basket. So it's very good to keep in touch with this channel. Now, what are we going to talk about today? Well, I'm going to talk about linear loading. It's something which I've used over the years, and it's a very interesting and valuable feature to introduce into your antennas. You know, let me explain. In antennas design, we very often talk about resonant frequencies because a lot of antennas are resonant, and when they're resonant they're easy to match with a bit of coax cable or whatever. So we say, for example, that our 20-meter dipole is resonant. Now, a dipole is a half wavelength, so therefore on 20 meters a half wave dipole is 10 meters. And we sometimes talk about quarter waves. So on the 20-meter band, we've already established that a half wave is 10 meters and therefore a quarter wave is 5 meters. Now, it's not exactly that. You need to apply a formula, but rough rule of thumb is that the 20-meter band, the wavelength is 20 meters long, the 40-meter band, the wavelength is 40 meters long, as you'd expect. Half wave is half that and a quarter wave is a quarter of that. Now, sometimes, I say sometimes, very often we've got small gardens, haven't we? And we think, wait a minute, we can't fit this half-wave dipole into a garden, or this quarter-wave vertical is far too high. I need to reduce it. And of course, if we reduce the length of an aerial, we change its frequency, which is not much good. If the aerial won't fit into your garden and you make it shorter, well, you made it shorter, it will fit, but it won't work because the resonant frequency will have shifted higher. As you shorten an antenna, so the resonant frequency goes higher, and vice versa. If you lengthen the antenna, then the resonant frequency goes lower. Now, one of the ways that we can actually counter the problem with the aerial being too long is to wind it up in the form of a coil. So let's take a half-wave dipole. A 20-meter half-wave dipole is 10 meters long. You've only got a garden that is 8 meters long, so you need to shorten it. Well, you can shorten it simply by winding it up a bit in a coil. And the traditional way of doing that is actually to make a small coil and put it in series with the aerial. Now, it doesn't actually matter where that coil goes in the aerial. It can go anywhere along. It can go at the point near the coax feed, or it can go halfway along, or it can go near the end. It doesn't actually matter, except, this is quite important, that the amount of windings on that coil has to be increased as you move away from the feed point, as you move away from the current point, the high current point on an antenna, which is very often the feed point. As you move along towards the end of the antenna, what we call the voltage point, because it's low current and high voltage, you need more turns to achieve resonance. The idea is that you put a coil in there, and that coil, although the antenna is now shorter, we've shortened the antenna, say for your 8 metre guard, we've shortened it to 8 metres long. We know it's not resonant on 20 metres anymore, but if we put a coil in it, we can actually bring the resonance back to 20 metres. So we've achieved what we set out to achieve. We've got a 20 metre half-wave dipole, 10 metres long, fitting into an 8 metre long garden. Now there is another way of actually making our antenna fit into the garden. This 20 metre half-wave dipole that's 10 metres long, and we reduce it to 8 metres. Instead of putting a coil in series, we can use something called linear loading. Now this is linear loading. I'll show you on the sketch here. This is linear loading. And what it is, it's really like a coil that's actually been expanded, and it simply becomes part of the aerial, and the part of the aerial is folded back on itself. Now we can actually do this at either end of the antenna. It's much easier to do it at the end of the antenna because you have to just have a single fold. If you use the same principle at the centre of the antenna, then you have to have two folds, and I'll just show you on the sketch here. So you have to have two folds. I'm sorry that the drawing's not very good, but you have to have two folds. So for ease of use or ease of implementing this, it's best to put the loading at the end. Now there's a limit to how far you can reduce an antenna using linear loading. Roughly, you can reduce it by about a third. That's the maximum you can reduce it if you have the fold back going all the way back to the feed point. And I've got a rough rule of thumb formula here. It's not precise, but it's a very good rule of thumb. It gives you some idea of what you need to do to your dipole or vertical in order to reduce the size. As a rough rule, you need more than you would for a resonant frequency. So for example, our 10 metre dipole, which is the resonant frequency for 20 metres, if we fold it back so that it's only 8 metres long, we've effectively folded 1 metre each end back. But we need a bit more than that, because when you fold an antenna back, you need to increase the length in order to preserve the resonant frequency. So it may well be that instead of having a 10 metre length of wire that resonates on the 20 metre band, when we fold it back, we have to have something like a 11.5 or even a 12 metre length of wire to bring the antenna to frequency when we fold it back. Best to increase the wire length beyond what you expect it to be and then trim it back. Now there's a very easy way to actually construct a end-loaded dipole. What you can do is you can use 450 ohm ladder line. Here's a piece of 450 ohm ladder line, and you see it's spaced, it's two wires spaced. Now we can very easily make that into a linear loaded end piece for a dipole. All I've got to do is to shorten one end, and I've then got a folded back piece, and then I attach some wire to the other end to complete the dipole. You can see if we add this ladder line, we actually create a fold, and it's a very nice and easy way to do it because the width of the fold, the width between the two wires, is maintained by the plastic spacing of the 450 ohm ladder line. A great way of folding back a dipole. Is there an advantage in using linear loading? Well, yes, there is. First of all, it's easy, but perhaps more importantly, it is low Q, which means to say that it doesn't dramatically affect the bandwidth. If you add an inductor, and that's a coil, if you add an inductor to reduce the length of your antenna, you actually raise the Q somewhat, and the bandwidth of the antenna is narrowed. But with linear loading, it has minimal effect on the bandwidth of the antenna, certainly far less than a lumped inductor. So linear loading is a very attractive feature, and of course you can use it in other ways. You can use it on the vertical element of a vertical antenna. You can actually reduce the height of the vertical antenna by folding a bit back, using a bit of 450 ohm ladder line. And you can also use it on radials. If you've followed my videos recently where I've said that it's best to have a vertical antenna off the ground, say 2 or 3 meters up in the air, you then need to form what we call a ground plane or radials. Well, sometimes those radials won't quite fit in the garden. So what you do is you make them shorter. And a nice and tidy way of making them shorter is to use linear loading at the end of the radial. Fold a bit back until it fits into the garden. Use 450 ohm ladder line because it's easy, it preserves the spacing. It's a very useful feature, linear loading. So in your next antenna project where you need to reduce the length of the antenna, consider linear loading. It's got a lot of pluses going for it. So thanks once again for tuning into this video channel. Don't forget the discount feature. If you go onto our channel and look at the videos, you'll see a video, or you should see a video there, which highlights the fact that there's a discount offer on. You want to go to the more recent one, check the dates. You'll see within the video there, we'll mention the amount of the discount and the dates and the important code. So there we are. Another advantage of keeping in touch with the Waters and Stanton video channel. We not only try to pass on some information, perhaps make it a little bit entertaining sometimes, but also we could save you some money. Keep in touch with the Waters and Stanton video channel. In the meantime, enjoy your hand radio, take care, and I'll see you in the next video.